Why Tesla and General Motors are different. Munro Associates tear down a pair of electric motors from General Motors and Tesla. What their engineers found are two completely different approaches to cooling. One prioritizes simplicity, while the other squeezes out efficiency using some surprising engineering. Cooling an electric motor seems like a science that we've had down for years. Just throw some liquid antifreeze through some tubes, make sure air is blowing through a sufficiently sized radiator, and everything is fine. But there's a fine science that goes into making sure each component is cooled to just the right amount and in the right places. Recently, Sandy Munro's engineering firm, Munro Associates, decided to tear down two electric traction motors. One is from a Tesla Cybertruck, and the other is from a Chevrolet Equinox, meaning that we're getting a taste of Silicon Valley's latest and greatest, as well as Detroit's take on making an affordable electric powertrain. The differences show that the automakers have wildly different strategies for cooling their drive motors. The technical explainer of the two motors is given by Munro's Paul Turnbull. He shows off the internals of both motors, as well as the various parts needed to cool them, and notes the trade-offs between the two platforms. Let's start with GM's approach to cooling the motor. Turnbull explains that GM's brilliance is in the simplicity of how it achieves cooling rather than use complex plumbing and pumps. GM uses the motor itself as kind of an ingenious gear system to fling oil upwards into cast channels that then use gravity to rain down over the motor. This cools the windings, magnets, and cast metal all at once. This method is cheap to engineer and simple because there are fewer moving parts to fail. It also doesn't require sapping additional power from the car's battery to run any external cooling hardware. More on this in a moment with Tesla's approach. It's also an old trick that Toyota used more than a decade ago in the Prius C. But this clever setup has limits. It's dependent on the motor speed, basically self-throttling oil when you're flying down the highway, but not so much when the motor is stationary in traffic. And if you're on a steep hill or thrashing around a track, the system's rainfall method of cooling can shift off target, which might not be ideal for an electric motor that can spin at speed of around 10,000 RPM. Tesla, on the other hand, uses a more precise method of cooling. It uses a high-pressure pump to force oil into channels, where it flows over specific components like the electrical windings and magnets to keep them nice and cool. This approach to cooling is also why Tesla can use cheaper neodymium magnets in its powertrains rather than rare earth metals. By not overcooling the motor itself, but rather precisely applying the oil to the points where temperature matters the most. Tesla's approach means that the motor's casing stays at a higher temperature despite its cooler internals. This increases the electrical resistance of the case and reduces the formation of eddy currents. Eddy currents, for those who don't know, are basically tiny whirlpools of electricity that occur as the magnetic fields from an EV motor changes while it spins. This isn't a problem unique to EVs at all, but we're talking about it today because EVs use magnets to power the drive motors. Every time the magnetic field flips within the motor as it turns, tiny loops of unwanted electricity are stirred up and bleed into the metal encasing components. These small fields create extra heat and waste energy, basically causing an efficiency problem that can be reduced by keeping the motor's casing warmer and naturally increasing its resistance to electricity. The trade-off is that the pump eats energy from the battery just to keep things cool. But so does the physical resistance created using GM's method. It is a bit more complex though, as extra machining is needed for the specific passages in Tesla's motor, plus extra parts, plumbing, and the pump itself. In short, GM is trusting physics while Tesla is trusting plumbing. But in a roundabout way, the more complex way, Tesla's way, is more technologically groundbreaking. It allows the brand to cut costs inside of the motor thanks to some funky electrical wizardry and squeeze out every extra ounce of performance. Both ways are smart, and both ways certainly work. If nothing else, it's proof that there are plenty of ways to go about achieving the same task in the E5 world, using wildly different methods. The question is, does the automaker prioritize efficiency or simplicity? That's what shapes the solution. Source: reposted and summarized from Rob Stumpf at insideevs.